Welcome to the deep dive. Ready to dive into some set theory? You sent over a section from a math textbook, and we're going to break it down, make sure it all makes sense.
Yeah, set theory. It seems a bit abstract at first, but it's super useful stuff, and honestly, you're already using it every day, you know?
Oh, really? I'm using set theory without even knowing it. How so?
Think about your grocery list. That's a set, right?
Okay, yeah, a list of things I need.
Exactly. Your workout playlist, that's a set too. The people you follow on social media, another set.
Huh. So it's just collections of things.
Exactly. In math, we call those collections sets. They can be anything. Numbers, letters, planets, you name it. As long as it's clear what's in the set and what's not.
So how do we describe these sets?
Well, one way is just to list everything out. It's called tabular form. You write all the elements inside curly brackets, like let's say the set of even numbers less than 10.
Okay, so that would be...
0, 2, 4, 6, 8, just like that.
Makes sense. But what if the set's too big to list everything?
Right. For that, we use set builder form. Instead of listing everything, you define a rule. So for all even numbers, you'd write x. X is even.
So it's like a filter, you're saying. You're not naming everything, but giving a rule for what's included.
Exactly. And that brings us to set notation.
Oh, yeah, symbols. I remember those.
We have a few key ones. There's a symbol that means belongs to, it looks like this. So if A is in set A, you write AA.
Got it. So what about if something's not in the set?
For that, we use A, which means does not belong to. If B isn't in set A, it would be BAA.
Okay, and I remember there's one more symbol, something about...
Subsets, that's A. If every element in set A is also in set B, then A is a subset of B. It's like a set within a set. And that's where those Venn diagrams come in handy.
Oh, yeah, those circles. I always like those. They make it so much clearer.
Exactly. The book has a good example where set A is completely inside set B. That's a subset.
So subsets are like those smaller circles nestled inside a bigger one in those diagrams. Now, the book also talked about finite and infinite sets. What's the difference there?
A finite set has a specific, countable number of elements. Like the alphabet has 26 letters. An infinite set, though, goes on forever.
Like all the even numbers.
Right, exactly. There's no end to that list. Now, when I was looking at the exercises, I noticed something. It mentioned the set of all even numbers and the set of all numbers. Aren't those both infinite? I mean, are there different sizes of infinity? Aha, good question. It turns out there are, but that's a whole other deep dive. Maybe another time. Let's stick with the types of sets from this section for now.
Okay, fair enough. So what kind of special sets are there?
Well, we have the null set, or the empty set. It has no elements at all. The symbol is imor.
Like the set of people over 200 years old.
Haha, exactly. Nobody in that set. And then we have subsets.
Right, like one set is inside another.
Right, like Russian nesting dolls. If everything in set A is also in set B, then A is a subset of B.
So that's where those Venn diagrams come in. They show us visually which set is a subset of the other.
Exactly. And then there are proper subsets, which means a subset that's not equal to the original set. So if B is a proper subset of A, it means B has some, but not all of the elements in A.
All right, so I think I'm starting to get this. The book also mentioned something about comparable sets and disjoint sets. What are those all about?
So comparable sets are when one is a subset of the other, or they're equal. But disjoint sets have absolutely nothing in common. If you drew them as Venn diagrams, they wouldn't overlap at all.
Like oil and water, they don't mix.
Precisely. And then there's this thing called a power set, which sounds kind of intimidating.
Power set, that does sound pretty intense. What is that?
So the power set of a set, we rate it as 2 to the power of s. It's basically the set of all possible subsets of s. It includes the empty set and the set itself. It sounds complicated, but let me give you an example. If we have a set M that just has A and B, then its power set would be all the possible combinations, AB, and the empty set.
Wow, that's a lot of subsets for just A and B. So why is it called a power set?
Because the number of elements in the power set is 2 to the power of the number of elements in the original set. So in our example, M has 2 elements, and its power set has 2 to the power of 2, which is 4 elements.
Oh, so it's like a mathematical exponent thing?
You got it. And remember those Venn diagrams? The book uses them to show all sorts of things like subsets, disjoint sets, and even sets that share some elements but aren't subsets of each other.
Right, like if you had the set of all cats and the set of all black animals, there would be some overlap with black cats, but neither set contains the other completely.
Exactly. Venn diagrams really help us visualize these relationships. Now, before we move on, the book briefly mentions axiomatic set theory.
Oh, that sounds complicated. Are we going full-on mathematician here?
Don't worry, we won't get too deep into the theory today, but basically, set theory, like other math, is built on these fundamental assumptions called axioms. They're like the ground rules.
Okay, so it's like the rule book for how sets work.
Precisely. One of those axioms the book talks about is the axiom of specification. Basically, you can define a set by taking an existing set and applying a rule to select specific elements.
So it's like filtering a set. Like if you take all integers and apply the rule is even, you end up with a set of all even integers.
You got it. It's a really important principle because it lets us create new sets from existing ones. And it just goes to show that even though sets seem simple at first, there's a lot more to them than meets the eye.
Back again for more set theory. We've covered a lot of definitions, notation, even those power sets. Now I'm thinking, how do we actually use all of this?
I'm glad you asked. It's time to see how set theory works in practice.
Right, what's the point of learning it if we don't know how to apply it?
Exactly. So think about other areas of math, like algebra. You work with sets of numbers all the time there, right?
Like the set of all real numbers.
Exactly, or the set of all integers. Understanding those sets and how they work is crucial for solving equations or figuring out functions.
Okay, so it's not just some abstract concept. It actually helps us do real math.
Absolutely. And it goes even further. In probability and statistics, sets represent events and sample spaces.
So like rolling a die.
Perfect example. All the possible outcomes, 1 through 6, that's a set. And then rolling an even number, that's a subset.
Oh, I see. So you're grouping possibilities into sets and then using set theory to analyze them?
You got it. And we're just scratching the surface here. Sets are used in computer science to organize data, in logic to build arguments, even in music theory.
Wow, sets are everywhere. I never realized how widely they're used.
It's true. And the more you learn about sets, the more connections you can make across different fields.
It's like a whole new way of thinking about the world.
Exactly. And a powerful tool for problem solving, too. Once you start seeing things through the lens of sets, you'll be surprised at the patterns you find.
I'm definitely feeling more set savvy after this deep dive. We've covered the basics pretty thoroughly, right?
Yeah, I think we've built a good foundation, but this is just the beginning. There's always more to learn, especially when you get into more advanced set theory.
Like those different sizes of infinity, that still blows my mind.
Yeah, that's a whole other rabbit hole. It really shows how deep and fascinating math can be.
Sets might seem simple, but they lead to some pretty complex stuff. So, are we ready to wrap things up with the final part of our set theory adventure?
I think so. Let's bring it all together and give our listeners some key takeaways and maybe some food for thought.
Okay, so back for the final round of our set theory deep dive. I gotta say, this has been way more interesting than I thought it'd be. I always thought sets were just kind of like dry, abstract math stuff.
Yeah, it can seem that way at first.
But I'm seeing now how they connect to so many things.
It's true. Sets really are fundamental to so many fields.
So as we wrap this up, what are the big takeaways? Like, why does all this set theory knowledge matter?
That's a great question. I think one of the most important things to remember is that sets give us a powerful way to organize and understand information. They let us categorize things, compare them, analyze them, all in a really precise way.
It's like a mental filing system.
Exactly.
Yeah.
And it's a system for, well, pretty much anything you can think of. This ability to categorize and classify, it's super important for thinking critically and solving problems.
So whether you're a scientist or a musician or, just living your life, this set thinking can give you an edge.
Exactly. It's about seeing those hidden patterns and connections.
I'm noticing sets everywhere now. The grocery store, my music library, even my to-do list.
That's great. You're training your mind to see things in a new way. And remember, we touched on how sets are used in so many fields.
Yeah, and honestly, it's kind of mind-blowing.
I really encourage our listeners to keep exploring. You'll be amazed how often sets pop up in unexpected places.
It's like a secret code for understanding the universe.
Haha, I like that. Now, before we sign off, I want to go back to something we talked about earlier. Remember those different sizes of infinity?
Oh, how could I forget? That one really got me thinking. Still trying to wrap my head around multiple infinities.
It's a tough concept to grasp, for sure.
It challenges, everything I thought I knew about math.
But it really shows how deep and beautiful math can be. Something as simple as sets can lead us to these incredible, mind-bending discoveries.
It's like there's always more to learn, more to wonder about.
Exactly. So as we finish up this set theory deep dive, keep that curiosity alive. Look for sets in your daily life, think about how they connect to other things, and don't be afraid to dive into the more challenging parts of the subject. You never know what you might discover.
Great advice. This has been an awesome journey into the world of sets.
I agree, it has been fascinating.
I feel like I've gained a whole new perspective. Thanks for joining us on the deep dive, and we'll see you next time.